Well, welcome back to our discussion of fractals. And we've introduced the new dimension to our science last time, and we'll apply it now to another example, deposition in particular, important example, and then we'll look at a classic question of fractal analysis, an interesting one. So let's get on with it. Okay, you've played with this, time to get to work again. Okay, so let's be engineers for a while. You have a problem. You want to grow by ballistic deposition. You want to grow a film, a thin film. And what we mean by ballistic deposition is that you have a hot filament, say, something like this, over a surface, and it's boiling off electrons or atoms around, and you want to, molecules, you want to distribute them on the surface below. Fine. And you want to have a model for this to see how the surface grows with time, where the particles are, how big are the irregularities. Okay, so we have a filament, it's evaporating, atoms, molecules, they're shooting out all over just from the thermal motion. Okay, so how do we model this? Well, we imagine if a particle hits a line someplace, it sticks. Okay, so otherwise, if they don't stick, you're not going to get a film. So we may as well go home and don't do that. Okay, so we have a line in our model here. We have a line down below with 200 sites. So we're doing a one-dimensional model here, but the atoms will grow upward. Okay, so the x values are random numbers. So we choose a random site out of the 200 someplace on this line. Okay, and then if there's a particle if a particle hits another particle that's sticking out like a sore thumb, it's going to stick to that particle, gets higher. If it hits another high particle, it sticks. Or if there's a hole here, someplace here, and the particle goes in the hole, it's obviously going to stay in there and fill up the hole. So rather than waiting forever, we speed up the simulation and say, okay, if there's a hole and the particle goes there, just fill it up so it levels out with its neighbors, because then it'll obviously fill out up until it gets there. So that's it. So that's the algorithm. Okay? So the algorithm here says pick a random number r, okay, any place between 0 and L, and then the new height will be the old height plus 1 if the new height is greater than what was either its neighbors, so it's going to grow. Okay? If it's a hole there, if h, the new place, the height when you go there, where the particle lands, is smaller than its neighbors, then just fill in the hole. Okay? Simple algorithm. And if we run the code here, so here will be the Python version of the code. We'll let it run. And it actually ran. It just was so quick you don't see anything. So what we have here is the height. Here are the 200 sites. And this is the surface we've produced from the bottom here all the way up. And you can see it grow if you slow down the algorithm. And you say, okay, it grows. If you measure it, it grows linearly in time, which is what you'd expect. And this is an example of the surface irregularities that are there. Okay? So if we look at this, we say, it's kind of interesting, isn't it? It looks sort of random, but then again, it repeats. It's almost like a coastline, okay, which has that combination of it. And if we smooth it out a little bit, give it some extra fuzz, it does look very much like a coastline. And of course, as we see in the picture on this next one, that's what many of the movie makers do when they make these artificial landscapes that look real, but they're obviously made by hands. They're made with a simple algorithm like this, but then smoothed out with this ray tracing program, as we've done here in our example. So let's look at the next slide, number 11. And here's one of the classic questions of mathematical theory and fractal theory. Mandelbrot in 1967 asked the question, how long is the coastline of Britain? Well, Britain's a small island. I wouldn't say the people are small-minded, but the island is small. And so you can ask, obviously if it's a finite small island, the coastline is going to be some number. It's not a big number, okay? Well, if it's Colorado or Wyoming, then it's easy to answer that question because they're square or rectangular states. and there's no natural boundary in the way of rivers or coasts, and so it's a geometric type figure. The perimeter is going to be a finite number, easy to calculate. The problem is that coasts are geographic in nature and not geometric. Geographic. So they're natural, and that's not a geometric object. So it's not an easy answer. Okay? But if you look at coastlines like we have here, like we had a model on the last, they appear to be self-similar. If you look at them smaller and smaller, they look the same scale, because whatever natural processes are forming them tend to do it in that kind of a way. So as our model for the coastline, let's say, a coast is going to be a fractal. And we'll use one of these algorithms, the one I just showed you, that models a surface. We'll use that as a model of a coastline and determine its fractal dimension. Okay? And then, once we have that model, we can use the length we determine, say that's the perimeter of the coast. So a little island could be that. So the first part of the problem is, okay, we need to determine the fractal dimension of the object. Once we have that, we can figure out, or better yet, look up, some mathematician who studied these things, what the perimeter would be for an object that has a certain dimension, and then deduce what the perimeter is. Fine. The problem here is we have a self-similar object. And do we know what the perimeter is for a self-similar object? Think of that Serempitsky gasket, which was more and more porous as we looked at it, had more and more little edges, and these little edges never seem to stop. So there's some challenge there. How do map makers do it? Well, if you were a map maker, imagine yourself walking along the coast of England, and what you would do would be, first you'd walk along, say, with a meter stick, put it down here, put it down there, put it down over there, all around, and you measure how many times you have to put down your meter stick, okay? And then you say the length of the coastline, L, is just n, the number of times I put down my ruler, times the length of my ruler. Fine. But then, what if I went back and I used a smaller ruler? Well, I'd put it down, I'd get, a larger number, but a smaller ruler size, and then I'd get another length, and then you'd say, aha, this is good. It's a more exact measurement because I'm getting all the curves. And then you'd say, okay, as the length of the ruler got smaller and smaller, as the length of the ruler approached 0, at least for a geometrical object, I get an accurate measurement of the length. That's fine. So in nature, however, what if the mathematicians who've studied this and the geographers who actually look at maps, what they find is that the length of a coastline is some constant m, we don't care about that, r, the length of our ruler, raised to the power 1 minus d sub f. Okay, fine. Well, that's good. The problem is, if d sub f, if the fractal dimension of the object is greater than 1, that means as you go to smaller and smaller ruler size, the length of the object, of the perimeter, goes to infinity. Does that make sense? Yes. Okay. So if it's a fractal object and you keep looking at it at smaller and smaller scale, but it's self-similar, each smaller scale looks like the bigger, it has an infinite number of details, infinitesimally small, it never ends. So the answer to the mathematical problem would be, if the coastline of England is fractal in nature, which is a good model, then it's infinite in length. Okay. But that's, of course, purely mathematical. You could say, wait. Mathematicians can remove themselves from the real world, but we're physicists. We can't do that. You could say, wait, if you keep looking at a coastline, sure, if you start measuring every pebble, you get a small number. If you break the pebble up, you get smaller and smaller at the atom level, but then you have quantum mechanics, okay? And at the quantum level, it's not continuous. Nature won't repeat itself there. It has well-defined structures. The atoms stop. Can't make the atoms smaller and smaller. So then the size must stop. Or you can go even to the gravitational general relativity level where you have a Compton size, Compton length, and you can't get smaller than that. So it could be that the length of Britain's coastline is a very, very large number, but not quite infinity if you're a physicist. But it's a good question. It's worth thinking about. So let's do the experiment. Okay? So here, slide 19, let's do some measurements, and we'll do a box counting measurement to determine a fractal dimension. So look at this slide a second. And this is the exercise we want you to repeat. Excuse me. It's a very nice exercise. We even have a code, an applet that does this for you. You could look at it. But it's just, it's nice to do. And I suggest you do it with a piece of graph paper rather than with just writing a computer program to do it, so you understand what's going on. Here's the whole idea. So we have here this surface, which we generated just with our algorithm for deposition, and we're going to cover the surface with different size boxes. And you just do that by taking a piece of graph paper. And you see here the, we can cover it with the big box, that's this length here, okay? That's one size. And so here's one big box we put on top. And here's another big box we've put on top. That covers the surface. Here's another big box. Okay, but there's something down below, so I have to make another box there. Here's another big box, another big box, another big box, another big box. Okay, so for a box of one length, which I know a large length, I need 1, 2, 3, 4, 5, 6, 7, 8 boxes. Okay, but now I say, just with a piece of graph paper, what if I use a smaller length? So here, if I have this smaller length, and I'm just showing you some of them here, here's one box, another box, another box, another box, etc. So you just keep track, and this is like using smaller and smaller rulers, exactly what it is. Okay? So then we go to the mathematics, and the mathematics tells us that the number of boxes needed to cover the surface, in other words, putting on top and not having every part contained within a box, is some constant times 1 over the ruler size, 1 over r, to the dimension d sub f. And d sub f is whatever the dimension of the object is. Usually, when one talks of graphs and maps, one talks about the scale of a map, and the scale s is just 1 over, or proportional to 1 over the ruler size. So if you want a very, if you go hiking, you want to see every little knob on the hill, you want a very high scale map. But if you're driving, you don't want that larger scale. So large scale means small sizes. Okay? Well, if the number of boxes is proportional to the scale, or to the df power, or 1 over the r to the minus df power, then if we take a logarithm of both sides of equation 1, we get equation 3, tells us that the log of the number of boxes needed, some constant which we don't care about, the fractional dimension times the log of the ruler size. Well, if we make a graph of the logarithm of n sub r versus the logarithm of r, what we have here is d sub f should be the, there should be a log here, log, or it's a log-log plot if you want. Okay? So on a log-log plot, log scale, log number, the slope will just be the fractal dimension. So what we get here in our analysis is we just do box counting, and on the graph we show you here, we tested it first. We just first took a square, a real square, and put different boxes on it, and this is the line we got, this nice red line here, and in fact, we get that the slope of this line corresponds to a dimension of 2. Interesting. If we took a straight line and put boxes on it, we would get a straight line has dimension 1. So the method works. If we take this figure on the left here, the coastline, and look at the slope of that, we get a fractal dimension of 1.3. So compare that to 1.6, which we deduced for the Serempsky gasket. Here we have a coastline. It's not, it covers space more densely than a straight line would. because it's greater dimension than 1, but it doesn't cover space nearly as much as the gasket, certainly not as much as a two-dimensional object, so it fills in space like a dimension 1.3 object. Okay? So if this was the coastline and it was really self-similar, it would be infinite in perimeter. So that's the exercise for you people to go do yourself. Any fractal you want. Do a tree if you want. Figure out what the perimeter of a tree is. Do box counting. I suggest doing it by hand because you get a feel for the different scales, and it's much quicker than writing a program. But some of you will write the program, but nevertheless. Okay, so now we learned about fractals. There's much more you can learn about them. People have published books on the different beautiful shapes, but for us, it's another dimension, literally another tool we have to analyze complicated behavior. Okay? So if we get results that look very complicated from your simulation, you can deduce its fractal dimension as we've done here. And if you get a number which is reasonable and consistent and you can repeat for other simulations, then you know, oh, there's some underlying structure here, and I can deduce what its fractal dimension is, and therefore it must be simple. It's not just random. So we'll now use these tools for other systems. You can go back and understand some of your nonlinear pendular plots using fractals. So enjoy your newfound tools. We'll see you next time. Bye-bye.